Okay, good day. This is Pre-Calculus Dual Enrollment. I am Mr. McCulley, and this is our lesson on our starting polynomial functions, specifically quadratic functions. So let's get right to it. Today we are going to analyze the graphs of quadratic functions. We're going to write quadratic functions in standard form, which is also known as vertex form, as well as general form. The easier, I guess not easier, but the more often seen form is the general form. And then we're also going to use quadratic functions to model some data. So let's get right to it here. The general form of a quadratic function is something that you have seen before. This is an Algebra 2 topic, so we're not going to spend a ton of time on it, but it is worth our time to review it. So it's y equals ax squared plus bx plus c. The degree of any quadratic function is 2. The number of terms are as many as 3, but there must be an ax squared term for it to be quadratic. If you have just bx and c, you have a linear equation. So you have to have something x squared so that it is a quadratic. The leading coefficient in this case is a. The constant term in this case is c. The linear coefficient in this case is b. And when I say a, c, and b, I'm talking about this a right here, this b, and this c. And then the linear term is bx, being that term. So those are some nomenclature for the parts of a quadratic function. If we want to visualize that quadratic function, we get something that looks like this. And the shape of a quadratic function, as if you remember, or hopefully you remember, is a parabola. And this particular parabola, we would say, opens up. It has an imaginary axis where you could fold along the axis and both parts would line up. That axis of symmetry is found using the equation x equals negative b over 2a. And when I say negative b and a, I again get those values from this general form. That a and that b finds the axis of symmetry. The zeros or the roots are up to 2 points where the quadratic, the parabola, crosses the x-axis. And we don't necessarily know what the x values are for those zeros or roots, but we do know that the y value is 0 in both cases. The y-intercept is 0c, and if you have a value that is on the y-axis, the x value is always 0. And if we go back to this general form of the equation, if x is 0, the first and second term are both 0, so all that's left is just c by itself. That is why the y-intercept is at 0c, and then the vertex is either the maximum or the minimum of the parabola. The second form of a quadratic that we're going to talk about today is the standard form, again sometimes called the vertex form, and that is y equals a times the quantity x minus h squared plus k. This a value for, if you have two equations of a parabola that are the same parabola, one is in vertex form and one is in standard form, then this a value here matches up with this a value here in the general form. All right, so when we look at this thing, h and k, those are the values of the vertex. Now in the general form, we have to do a little bit of work to get the vertex, but in the vertex form, we get the vertex out of it right away. Now here are two simple examples that don't necessarily look like a standard form, but they are. In this particular case, the vertex is, well, in the the standard equation here, we get x minus h. Well, to get a plus here, that would mean that the h would have to be negative. So I would have x minus negative 4, simplified would be x plus 4. So the h value is negative 4, and we see that there is no plus k. And so when there is no plus k, we're going to put a 0 there for that. So there's the vertex. And in this particular instance, we see that there is no h, there is no quantity that is being squared, it's just the x. So in that case, the h value is 0, and in this case, the k value is 3, so the vertex for that is as written. Okay, so let's talk about how to find parts of a quadratic in either form. When we're talking the general form, we've already talked about how to find the y-intercept. It's just going to be 0, c. And the axis of symmetry is x equals negative b over 2a. And then to find the vertex. Now this is the hardest part of using the general form, is going to be finding the y value of the vertex. I've got a message. So to find that, what you're going to do is you're going to plug the value of the axis of symmetry into the equation, and then you're going to evaluate for y. So the vertex is going to be negative b over 2a, comma, the function value of negative b over 2a. All right, so we think of this, there's my x value, there's my y value. Now, in vertex form, finding the vertex is the easiest part. It's just hk. The axis of symmetry is not that much more difficult. It's just x equals h, and that's the same as it is here. In this case, we have to find the axis of symmetry first, and then once we use that, it becomes the x value for the vertex. And so if we know what the vertex is, then the x value of the vertex has to become the axis of symmetry. And then to find the y-intercept, we let x equal to 0 and evaluate for y. Now, in this particular instance, it's exactly the same thing that we did here. It's just that because these two terms will always be 0 for y-intercept, we just make a shortcut and say z, say it's c. All right, whereas this one, we'll actually have to plug in 0 and do some calculations, especially if there's a minus h there. All right, moving on. The value of a, and again, in both versions of the equation, right here, we do have that a value, has the most influence on the shape of a quadratic. If a is greater than 0, then the quadratic opens up. If a is less than 0, then the quadratic opens down. The closer to 0 that the absolute value of a is, because it could be positive or negative, the wider the quadratic is. And the larger that the absolute value of a is, so like negative 10, when you make it absolute value, we would consider that a large value, the narrower the quadratic is. And so we can do a real quick, let's clear this out. Let's just use x squared as our general quadratic. It doesn't have a linear term, but we'll do something simple just because we want to see how a affects the shape of the graph. So here is our standard graph. If we want to make the function open down, we make a negative, and we're just making it -1 in this particular case. And so clearly it opens down in there. Now, if we want to make the function a little bit wider, what we're going to do is we're going to make a very small. So if I make a like 0.1, and then it'll be x squared like that, 0.1 x squared, a small value for a, we can see that that graph gets a lot wider. Now, if I make, say, if I make it, let's delete there and make it, say, 6, all right? Let's say it's 6x squared. Well, since 6 is bigger than 1, it's going to make that graph a little bit narrower. It actually is of a vertical stretch by a factor of 6, but that's kind of besides the point. All right, so we did that. A couple of examples to get through. Describe the graph of the function, identify the vertex, the x-intercepts, and then we'll use a graphing utility to do all those things. You need to be able to do both because we need to be strong in both our use of algebra as well as being able to use technology. So if I say f of x is equal to negative x squared plus 3x minus 4, I could distribute the negative and say that it's negative x squared minus 3x and then plus 4. We could use either one if we wanted to. And so I want to describe the graph of this function. Because the leading coefficient is negative, it opens down, and because we have an x squared term, we will say that the graph is a parabola that opens down. All right, identify the vertex and the x-intercepts. Okay, well, we can do that too. So let's use this second form to identify the vertex. And since it's in general form, we're going to use the x equal to negative b over 2a. And in this case, negative 3 would be positive 3 over 2 times negative 1, which is going to be negative 3 over 2. And so if I want to plug in negative 3 over 2 into this function, its fraction, just for expediency's sake, second quit is what I want. There we go. Let's clear this out. It's negative 3 over 2 is negative 1.5. Negative 1.5 quantity squared minus 3 times negative 1.5 and then plus 4. And because fractions are better for our answers, we're going to hit the math button, and the first value, our first function is the fraction function. And so we get 25 over 4. So let's see, 6 3/4 ish. Yeah. So our vertex is, we said it was negative 3 over 2 and then positive 25 over 4. Right? Pretty sure that's what we got. Last one. Let me check. Yep. Okay. So there's our vertex. Our x-intercepts. Well, it's what makes this thing 0. And we can factor either of them if we wanted to. And here's, I'm going to erase here because I'm going to use that first part. So if I go f of x equal to negative x squared plus 3x minus 4, your first try should always be to try and factor this thing first. And so all I have to do, because the leading coefficient is 1, is say I need 2 factors of negative 4 that add up to 3, and that's pretty easy. I get x, I need a plus 4, and then an x minus 1, negative 4 positive 4 and negative 1 add up to positive 3, and then 4 times negative 1 is negative 4, so that's going to work out for us. So our x-intercepts are going to be everything that makes the function equal to 0. So we've got 2 possibilities here. So what plus 4 is equal to 0? Well, negative 4 is plus 4 is equal to 0. And what minus 1 is equal to 0? Well, 1 minus 1 is equal to 0. So there are our x-intercepts. So we want to use a graphing utility to do those same things. And so we're going to go back to the graphing utility, hit our y equals. We're going to clear out the stuff that we had in there before, and we'll type it in just as the book had it and have it negative quantity x squared minus 3x plus 4. I think that is the way. Let's check and make sure. No, it should be plus 3 and minus 4. So that would be a mess up. Plus 3 minus 4. We hit graph here. And so if we're asked to find the vertex, that is a maximum of this polynomial function. And so remember, that is the second function of the trace button. So second trace, we'll do a 4 to get a maximum. And remember, they were going to want us to open up an interval. So we're going to start with a left bound, hit enter. And then we're going to go over to a right bound, hit enter. It asks us to guess, but we don't care. So we're going to hit enter, and we get negative 1.4999. That thing will round up to negative 1.5, which is what we said. And then 25 over 4. 4 goes into 25 6 times with 3 left over. No, with 1 left over. That's right. And so we get 6.25, which is what that would be. So that matches up as well. To find y-intercepts using the graphing calculator, we can go second, we can hit the trace button, and we can use this 0 feature. And I'm not going to do both of them, but let's at least find one of them. So we're going to do 0, we're going to hit 2. And so just like we did to find the maximum, we're going to set up an interval where the calculator is going to look for a change from positive to negative, and it's going to try and zoom in on that. So the left bound of where one of these is going to be right there, and then the right bound would be right there. We hit enter, and 1, 0 is one of the x-intercepts. And so if you want, I'll let you solve for the other one, but it's the exact same process. All right, the next thing, completing the square review. They are going to ask you a couple of times to change the general form of a quadratic into standard form or vertex form. And so I like to review completing the square. And again, we did this in Algebra 2 last year. So the first thing, here is my quadratic function that I'm trying to change to standard form. The first thing we need to do is make sure that the a value is equal to 1. So to do that, what I'm going to do is I'm going to factor out a 2. So I'm going to go y equals 2 times the quantity. And so 2x squared divided by 2 is just going to be x squared. 4x divided by 2, or I gave it away. 8x divided by 2 is going to be 4x, and then negative 14 divided by 2 is going to be 7. You know what? Let's do it this way. Let's leave that negative 14 out there. I think that's what we're going to do. We're going to separate, we'll move the negative 14 over, and we'll just leave some space to complete the square. And so to complete the square, what we're going to do is we're going to add and subtract b over 2 quantity squared from the same side. So y equals, we're going to do the 2, and we're going to do x squared plus 4x. Now our b is equal to 4, and so half of that would be 2 squared. And since it's inside the parentheses, the distributive property says that I would have to distribute that. So I actually have 2 times 2 squared. And so since I'm adding 2 times 2 squared, and I want to keep everything on the same side, I must also subtract away 2 times 2 squared from that side. Now this thing is a perfect square, and the way that I remember it is I just bring down the x, I bring down the positive 2, and I put squared around it, and then negative 14 minus 2 times 2 squared is 8, so negative 14 minus 8 is going to be negative 22. And we'll put a box around that, and that will be our standard form. And so we could read a lot from that. Our vertex would be negative 2, negative 22, which works. And then we could find our y-intercept by letting x equal to 0. All right, so I think this is one of the last things. We're on our last review things, the quadratic formula. You can use the quadratic formula to find all of the zeros of a quadratic polynomial. In this one back here, I did use factoring, and usually, just as a rule of thumb, I say if the a value is 1, try and factor it real quick. But as soon as the a value becomes something other than 1, we're going to use the quadratic formula. And we spent a lot of time deriving the quadratic formula in Honors Algebra 2. Today I'm just going to try and review and remember. So if you have ax squared plus bx plus c equal to 0, then the values for x that makes this statement true are negative b plus or minus the square root of b squared minus 4ac all over 2a, where b, a, and c are all the values that are coefficients and the constant term from that equation. So just a real elementary example, if I said find the zeros of f of x equals x squared minus 3x plus 5, that might come out. we can use the quadratic formula to do that because we want to know where the y values are equal to 0. So here's what I'm going to do. Negative b will be positive 3, so x equals 3 plus or minus the square root of negative 3 squared minus 4 times a. A is 1. And then let's see here, c is 5. And I have a feeling that this is not going to be the example that I want it to be because it's going to have an imaginary number. So we're going to call an audible real quick here, and we're going to make this a negative 5. I'm not ready to talk about imaginaries. We'll talk about that later. And so we'll change that c to negative 5 there, all over 2. Now this we're going to want to simplify. So we've got x equals 3 plus or minus the square root of, remember, when you square a negative in your graphing calculator, I get this error all the time, and I'm trying to keep you from making that error. When you square a negative number in your graphing calculator, please make sure you put parentheses around it, because we know that negative 3 times negative 3 should be positive 9. But if you just go negative 3 squared like that, it gets negative 9. Now the reason that is this follows the order of operations. Exponents are above multiplied by negative 1. So if you want to square a negative 3, make sure you put the parentheses around it so we get that positive 9 there. We don't have to do that, but we can do it in our head. So let's see here. Negative 3 squared will give me 9. Negative 4 times 1 times negative 5 will be positive 20. All over 2, and I get x equals 3 plus or minus the square root of 29 all over 2. Now this is a good answer, final answer, and we know that because the square root of 29 is irrational. So it'll just be a 2 R's, I think, irrational. There we go, 2 R's. It's just going to be a decimal value. So when you can't simplify your radicals, you're just going to leave it. 29 is a prime number. If you get a square root of any prime number, you know that you're done. Okay, finally, a exploration problem, application problem. This comes from the text. It is on page 97, number 64. It says a child care center has 200 feet of fencing to enclose 2 adjacent regular safe play areas. See the figure? Use the following methods to determine the dimensions that will produce the maximum enclosed area. So before I get started, I actually have to draw the picture that they gave. So it's not too bad. We have, come on, there we go. I want a rectangle. That's a square. Don't want that. Here's rectangle. Okay, so I got a rectangle, and then I need a line to go from here to here. And they want it to be equal. That's pretty close, but let's see if we can. That will be close enough for government work. So let's go back to this. And in the diagram, this is the base of our play areas, where they say this is x, and this is y. And so they say write the total area A of the play area as a function of x. Now, if they're rectangles, and I have x here and I have x here, then we'll have x here and x there, y there and y there. So they want us to determine area. Well, I got 2 variables. That makes it hard. So what we're going to do is we're going to use the secondary information. And a secondary function can be a lot of things. In this particular case, it's perimeter. And so I can say that, let's see here, if I add all these up, that the total perimeter, the 200 feet, will be equal to, let's see, 1, 2, 3, 4x plus 1, 2, 3, 3y. And we're trying to maximize area. Area in this particular case would be 2x times y, length times width. So x and x, that's going to give me 2x because we're adding them together. And then the width is just going to be y. We're going to assume that that width there is negligible, and we're not going to count it. So let's see here. First question A, find area, area, in terms of x. Well, I currently have area in terms of x and y. And so here's what I'm going to do. I'm going to solve this function right here for y. Get y by itself. I'm going to cheat and do that real quick in my head and say that y is equal to 200 minus 4x all over 3. And so we're just going to plug that into that equation. We'll say a equal to 2x times 200 minus 4x all over 3. And then we'll distribute that 2x, and so we'll have 400 over 3x minus 8 over 3x squared. And so there's our equation for A. That works. It says use a table feature and a graphing utility to show the possible values of x corresponding to the area, and they want us to use a table feature. We're not going to do that because we have a fairly exact measure. And so if I hit clear and I go, let's see here, one more time. So 400 over, okay, so just reviewing some fraction stuff. If you hit alpha and then y equals, you can do a fraction. So we're just going to hit a 1 there. And we're going to go 400 over 3, and then we'll hit the right arrow on the D-pad to go x, and then minus, again to get a fraction, alpha, y equals, hit 1, 8 over 3, and then this is going to be x squared. Oops, I don't want that. X squared. All right, so now if I graph this thing, I really am not seeing a whole lot going on here. I see this, but if we go back to our y equals, clearly this is going to be a parabola because of the x squared, and it's going to open down because of the negative 8 over 3, the negative leading coefficient. So I know that the graph has to look something like this. It has to. And again, because x and y have to be positive because they represent positive distances. So I have to have something that looks like this. So when I want to change my window, I hit the window button. We definitely need to see more of the x values. And so let's make it, let's start with 200. That's a reasonable guess, I guess. And then we're talking area, so area gets big really fast. Let's make it 2,000 as a first guess. And hit graph, and see what we get. Oh, look at that. That's reasonable. I made my x's too big, but there's my values there. And so if I want to find this highest value x, for x, again, I go second, I hit the trace button. We're going to do a maximum, so I go to 4. We're going to go left a little bit until we get it. And so I'm looking at this. I'm looking at this value here and seeing that it's coming up as I get closer. And we move to there. We're going to hit enter. We're going to hit a right bound right there. Hit enter. We're going to get enter. So our maximum, it looks like to me that our maximum value, we've got an x value at 25 and then 1,666 and 6 repeating. So this point right here is 25 and then 1,666.6 repeating. That's what we have. And so we need to talk about how to label these two axes. This axis here is the x values. So it's this length right here. This quote unquote y is now, look, we have over here, it's area. All right. And so basically what we can read from this is we could say that at a length th of 25, and I'm pretty sure it's feet. I want to make sure I have the right 25 feet. We can enclose a maximum area of 1,600 166.6 repeating feet squared. Now that's how we do it using a graphing calculator. Well, how will we do it by hand? Well, remember, this point right here is a vertex. And we have a way to find a vertex if it's in the general form, and that's what it is. So if I go x equals negative b over 2a, negative b would be negative 400 over 3, and 2a would be 2 times negative 8 over 3. So simplifying the bottom, when you multiply fractions, remember 2 is 2 over 1, so I multiply the numerators and the denominators, I would have negative 400 over 3 all over negative 16 over 3. So if you divide fractions, a fraction divided by a fraction, you multiply the numerator by the reciprocal of the denominator. So I have negative 400 over 3 times 3 over 16. And remember that the 3's cancel. And I would have a negative here as well. So negative times a negative is positive. 16 goes into 400. Well, 4 divides both of these. 4 goes into 400 100 times. 4 goes into 16 4 times. So I'd have 100 over 6 or 100 over 4. Sorry about that. Let's do a better job. 100 over 4, and then 100 divided into 4 would be a quarter, 25, and notice that's what we got right there. And so if I took that 25 and I plugged it back into the original equation, I would get this 166.66 repeating. Well, folks, that's all I got. So the Star Wars fun fact of the day: Alec Guinness played Obi-Wan Kenobi in Star Wars episodes 4, 5, and 6. He had won the Academy Award for Best Actor in 1957 for a part that is shown here in the picture, Bridge Over the River Kwai. And George Lucas tried to get him because he was trying to add some depth and quality to his picture. And so to get him to play it, Alec Guinness thought that the movie Star Wars was just fairy tale trash, so they offered to give him 2% of the gross receipts, and he took it because that's that's actually a huge deal, thinking that Star Wars would not have been a big deal. And by the time he died, the gross receipts of Star Wars, that 2%, actually earned him $97 million. Not bad for about 5 years worth of work. All right, that's all I got today, folks. See you next time. Bye.